This video cross-examines the official story of the world's tallest tower against the hard limits that decide if it stands or fails. The official line is simple. The Burj Khalifa rises 828 meters and rests on a piled raft designed for roughly 500,000 metric tons, and that is sold as complete. The first hard check is to hold that neat claim against the site reality of about 40 meters of sand above more mixed soils by mapping the actual load path pile by pile under real weight. Look, do the simplest check. If a foundation meant to act like one solid body must rely on 192 piles threading through shifting sand to variable layers, how can the tail of a steady base survive ground that, by its nature, is not steady at all? We are told 192 reinforced concrete piles run about 1.5 meters wide and push to about 50 meters depth, which sounds bold. The shop floor test is dirty but clear. Mark every pile, drill side cores around a sample set, and match as-built soil contacts. To the design boring logs, to see if each tip kissed the intended layer or stopped short in a softer pocket. Think. Reality does not care. If even a handful of piles sit a touch high or bite into a layer that was missed in a borehole, does the claimed neat load share hold? Or does the job tilt into roulette, where a few bad bites carry more than they should? The story says capacity comes from end bearing and from friction along the pile shafts in carbonate soils. The verification is to jack a sacrificial test pile in stages and watch displacement against expected friction curves at the target depth. Then compare those curves to strain gauges on working piles under live load. Be honest. Count it or cut it. If the test curves sing in a lab rig, but live piles slide more than predicted when the tower warms, cools, and sways, is that robust friction or a fiction crafted by spreadsheets? We hear the tower does not float in sand, but is anchored through about 40 meters of it into more stable soil layers below. The quick constraint check is settlement truth. Set a grid of precise leveling points across the raft and track any zones that sink faster than neighbors as levels, seasons, and fit-outs add mass. Look, you cannot cheat constraints. If stable is just a word, and the SAG map shows slow drift on one wing, does the claim of a calm base stand or fold under its own weight? The mass headline, about 500,000 metric tons of concrete and steel, sounds like a single number. The real check is to follow motion through time by logging sway, thermal stretch, and vibration envelopes, and lining those up with foundation strain so you can spot any piles that take a ratchet hit with each hot day and gusty night. Think. Physics cashes the checks. If the math closes only for a static paperweight, while the real tower flexes day and night, is that a solved base or a moving target painted as steady? Finite element models were run, and papers exist for that exact tower. The shop truth check is to pry open inputs and ask if concrete batches were treated as one clean strength, and whether the carbonate layer near 50 meters was drawn as one smooth, gap-free sheet. Look, stop buying it. If the model eats perfect inputs while the ground delivers noisy reality, do safe outputs map to the tower or to a tidy ideal that never lived under the raft? The public hook is the Y-shaped buttressed core that confuses the wind. The check is to stack wind tunnel curves on small, rigid models against full-scale sway and acceleration logs over years, and ask if vortex patterns align or drift when desert gusts stack weird. Be honest. Measure, then believe. If the tunnel tune is crisp, yet the live tower hum carries a sour note on certain angles, is the shape ruling the air, or is that story nonsense when the sky misbehaves? When shape alone cannot hold sway to comfort, the official line points to tuned mass dampers near the top with hydraulic guts. The hands-on check is to drill faults, pull power, spoof a sensor, force a leak, and then watch the tower's response trace to see if the damper fails safe or swings off script. Look, what breaks first? If long-term steadiness leans on moving parts that need care and juice, is that permanent strength, or a delicate brace that opens one more door to lose control? Project notes say predicted settlements sit within safe limits. Neat words. The field reality check is to measure differential settlement with lasers, GPS, and embedded strain, and then compare drift against those sensors' own heat drift, so you can strip noise from real lean. Think. Do the simplest check. If green lights come from tools that wander when heat kicks them, are we seeing truth, or a dashboard groomed to match the story? We are told the structure streams real-time data from GPS, lasers, and strain gauges. The constraint check is that each device has tolerance and drift, so you push known calibration steps at known times and match those stamps to logs across hot and cold to prove the system can see a millimeter-scale tilt under desert swings. Be honest. Count it or cut it. If the eyesight blurs when it is hottest and the building strains the most, does a clean dataset prove safety or just coat a tail? We have the pile count and the depth, so those piles took mountains of high-performance concrete in hot days. The site check is to track pour timing and batch heat, then cross those with curing logs to see how many pours ran close to thresholds that invite deep microcracks or cold joints. Look, you cannot cheat constraints. If even one buried pile hides a hot core or a weak bond that nobody can ever open again, are we still in flawless land? Or did we plant a bad tooth you will never pull? Concrete chemistry needs time, cooling, and moisture to hit target strength. Yet the timeline pushed forward. The plain test is cylinders from each batch, crushed on schedule, then paired with in-place thermal traces to flag batches that cooked too long while trapped deep. Think. Measure, then believe. If lab proxies passed while the buried mass lived a different heat life, is a pile that looks fine on paper still fine at noon in a blazing summer? Downtown Dubai was the prize, a strategic zip code, so the risk was worth it. They say, the constraint check is to compare that choice against the simple fact that other very tall towers often chase sites with shallow, hard layers to cut time and risk. Then ask why this plot that needed 50-meter piles through 40 meters of sand was crowned. Be honest. Prove it under load. If there were easier grounds and the pick still went to a harder site, is that routine logic or a demo staged no matter the base? Any seasoned builder will tell you that chasing the tallest badge bends what risk folks accept. The test is incentives. Line up that world record goal next to the acceptance of tuned machinery, deep piles, and an exotic Y-shape. Then ask if prestige turned the knob on what odds were stamped good enough. Look, who benefits? If the prize is global icon fame and the path is risk on gear, is simple commercial project a fair label or a costume? We are told it is a commercial success, which, sure, in public terms holds. The constraint check is whether profit alone explains why the base, the concrete, the braces, and the wind dodge ran outside comfort, because profit usually picks repeatable moves, not one-off bets. Think. Stop buying it. If the chart was only leases and sales, why does the risk sketch read like a lab run dressed as a tower? Again, the piles lean hard on shaft friction as a major share. The time test is to trend friction proxy by tracking long-term settlement under steady load, and watch if the curve flattens or crawls as soils squeeze or as groundwater drifts. Be honest. Reality does not care. If grip today is not grip in 50 years, are we counting on a hold that relaxes while the story stays frozen? Factors of safety are cited, which is standard. The hard check is a narrow cut already on the table. If in 50 years the aquifer drift shaves just 10% off friction capacity, do logged strains and settlement creep eat into the cushion, or hold the line without flirting with red? Look, do the simplest check. If a small, real-world shave can gobble the buffer, is this safe by design or safe by hope that the ground never changes? We are told the geology is suitable once you pass 40 meters of sand into deeper layers. The field check is to count risk tokens by listing every added step, drill, case, steel, pour, cure, that must go right to touch that deeper layer with no hidden flaw. Think. Count it or cut it. If suitability arrives only after a gauntlet where one permanent miss lurks in the dark, is suitable honest or a semantic trick? Geotechnical papers gave a green light, but with caveats, not love notes. The verification is paper to site. Read those reports beside the means and methods logs to see whether the cautious tone matched the on-site steps, or if the public talk shaved off the caveats. Be honest. You cannot cheat constraints. If reports say, possible with extreme care, and the billboard says, routine and proven, which voice maps to the ground under the raft? Wind tunnel work endorsed the Y-core under controlled flow. The check is to let the live tower speak. Stack wind speed, direction, and gust on storm days against measured sway to see where real air left the model's tidy map. Look, prove it under load. If outliers pile up, does confuse the wind hold, or play like marketing gloss slapped over hard turbulence? The comfort promise leans on tuned mass dampers, hydraulics, sensors, and code. The constraint check is upkeep truth. Pull logs for downtimes, fault alarms, and response windows during gusts. Then see if the system stayed sharp or slid into sticky valves and laggy eyes. Think. What breaks first? If long life needs perfect tweaks and constant juice, is that bedrock or a bandage that can peel? We are told the measurement backbone, GPS, lasers, strain gauges, keeps live watch. The check is disagreement hunting. Compare sensor families on hot and cold swings, and cross those with old-fashioned leveling shots to call out the first tool that drifts. Be honest. Measure, then believe. If the eyes do not agree in heat, Are green bars comfort or mirage that moves with the sun? The soil and structure models are central to the tale. The field check is to match the predicted settlement bowl and stress fields to hairline crack maps in non-structural finishes, and to faint patterns in base slabs that betray where weight really traveled. Look, reality does not care. If the crack atlas does not rhyme with the bowl the model drew, are we worshipping equations or reading the building's letter back to us and choosing to ignore it? Public talk frames each advanced part as off-the-shelf. Y-core, strong concrete, deep piles, dampers, done. The check is redundancy. List passive measures that hold sway if dampers nap, and then ask if the core alone covers the worst gusts seen so far. Think. Count it or cut it. If backup is thin and the front line moves, is that robust strength or a delicate dance masked as routine? The soil profile is often drawn as tidy layers. The hands-on check calls out variance by logging drilling returns and torque changes as tools drove down, then flagging soft pockets that the initial borings did not catch. Be honest. You cannot cheat constraints. If crews felt change on the way down, does the neat layer tail hold? Or did we gloss wrinkles with a pretty section drawing? We keep circling it. 500,000 metric tons on a small footprint. The check is load path discipline. Map where every added ton from fit-outs, water and people actually sits, and ask if the model counted those masses in the right wings. Look, who benefits? If live loads cluster off-center and drift grows, is the tidy total still a comfort blanket? Or does concentration turn safe math thin? There is a lure of scale. We knew how, we just did bigger. The constraint check is to find where scaling snaps by setting tricks that worked short against a sky-high stack, where creep, fatigue, and heat pulls longer and harder. Then see which small world rules bend when stretched. Think. Physics cashes the checks. If yesterday's rules droop under today's span, is it fair to call this a straight replay? Or is that claim absurd? We hear settlement has been within the safe limits so far. The check that matters is slope, not just total drop. Plot settlement speed and ask if the rate is flattening or if a corner keeps sinking in little steady bites. Be honest. Measure, then believe. If the slope is not near zero, is comfort in a small total slump honest? Or is a slow lean just delayed pain? The core plus outrigger scheme is supposed to steer both wind and gravity. The field check is to read strain at those link points when gusts hit and see if the planned share passed clean or if load hopped side to side in bursts. Look. Do the simplest check. If energy jumps around when air gets messy, does the predictable path claim hold? Or is the true script spiky and off-plan? Engineers say the system was known and executed with care. The biting check is build variance. How tight were rebar and cover in deep piles? And how many placement hits sat near the allowed edges based on as-built records? Think. Stop buying it. If day of placement drift lived near limits, is that a cushion or cliffside footwork sold as a stroll? We are told factors of safety and lab work back the story. The ground truth check is heat, time, and cycles. Review how concrete aged in hot-cold swings and whether compressive strength growth tracked lab curves or lagged in deep, warm cores. Be honest. You cannot cheat constraints. If mass matured slower or uneven under sun and sand, is a neat lab curve an anchor or a forgery of how the base behaves today? Public messaging stays calm, routine, controlled, predicted. The reality check is to stack the official fault list already named. Hydraulic leaks, sensor slips, software bugs, power loss, against logs to see how often each fired and what the tower did in those gaps. Look, prove it under load. If worst-case items are logged events, is the calm tone honest or cosmetic paint on noisy truth? Wind tunnel work is pushed as settled fact. The pressure test is time in service. Log one storm season against the next. Match larger responses to changes in upstream structures or sea breeze shifts. And check if the same wind now pushes harder as the city fills. Think. Physics cashes the checks. If the air around the tower changes while the model stays still, can an old tunnel run still be the last word? The site choice keeps nagging. The motive check is alignment. Line up the tallest title chase, the 40 meters of sand, and the big talk about innovation. Then ask if the project was shaped to prove capability more than to pick the simplest return. Be honest. Who benefits? If the incentives fit a flashy show, a force, does just a profit move ring true or thin? Here success proves the approach. The constraint check is survivorship bias. Count not just that it stands, but how tight the winds were. By listing all steps where a miss would be buried, cast, and logged. Look, you cannot cheat constraints. If the path was no do-over narrow, is the smooth narrative a fair mirror or fiction that hides how slim the window was? The official voice keeps calling the parts established. Y-core, piles, dampers, strong concrete, as if they came off a shelf. The stress test is uniqueness. Ask how many jobs used this exact combo at this scale in desert heat, and the answer is almost none. Think, measure, then believe. If almost no one had done this set at this size, is established practice anything but absurd spin? We keep hearing the soil layers were mapped and known. The workbench check is absence. Match install surprises like stuck casings or sudden loss of fluid to logs, because such blips mark ground not as drawn. Be honest. Stop buying it. If the build met surprises the paper missed, is "we knew it all" possible in practice? Size is sold as manageable with clever design. The constraint check is material truth. Gravity, wind, heat, and tremor do not scale down with charm. So ask whether each load was counted more by passive form or by active gear that can quit. Look, reality does not care. If much of the margin rides on machines, is that actual stability or borrowed calm on a good day? We are told everything was measured, controlled, and consistent. The gritty check is variance. Hunt for widest spreads in any monitored value and see if design margins swallowed those with room, or if peaks scraped the ceiling. Think. Count it or cut it. If the far edges already grazed limits, is the comfort talk honest or just fiction with a straight face? The site's 40 meters of sand is pitched as a traversed layer. The practical check is hands-on. Each meter of sand adds risk for wall collapse during casing and robs heat during curing. So see if schedule leaned on night pause and extra cooling to keep pause alive. Be honest. You cannot cheat constraints. If the build had to kneel to weather to pour a hidden forest of piles, is no big deal credible? We hear a 100-year life is the life plan. The midlife check is straight. Projects that last that long need quiet years. So hold the 10% friction loss scenario against settlement trends and damper reliability so far, and ask if the path to that age is smooth. Look. Do the simplest check. If the curve today hints at drift, is the century claim real or sales talk? Official lines suggest shape and support solved the wind. The check is human comfort. Flag any sway-related closures on top floors and match those to damper runs. Then ask if comfort is mostly machine-made. Think. Prove it under load. If comfort rides an active counterswing, is the base design alone enough? Or is a device carrying the promise? We are told other megatools chase shallow, hard layers, while this one did not, making this an outlier. The check is humility. Comb the record for clear statements of unknowns and contingency plans, not just glossy certainty. Be honest. Measure, then believe. If the message hides unknowns and beams certainty, does that feel like science or a forgery of confidence? The brand line says, "Modern engineering tamed chaos." The field check is what changed on hot days or windy spikes. Did pause pause? Did crews shift to night? Did gear get staged for heat? Because choke points reveal the true constraints that slogans cannot dodge. Look. You cannot cheat constraints. If the site bent the knee to the weather to keep tolerances, is the myth of total control anything but nonsense? The account claims a clean chain from soil report to model to build to monitoring. The reality check is seam hunting. Find disputes between model and measure that were fixed by massaging inputs after the fact instead of changing the build, and see if the fit came from physics or from desk edits. Think. Stop buying it. If the match came from tuning the model, is predictive earned or retrofitted? By now the pattern is loud. The tail is tidy. The ground is not. The hard check is coherence under constraint. Do the parts still add up? If one proxy blurs, one machine sleeps, or one ground layer waves off the plan, be honest. Physics cashes the checks. If the story holds, only with 0 misses, over a chain this long, is that engineering or a fairy tale for adults? Here is one more angle on the piles. Groups of piles never act like singles. The check is group behavior. Compare settlement under the raft near cluster edges to centers, and map strain bridging across neighbors to see if some piles are stealing load. Look. Do the simplest check. If a few piles in the corner take extra bite while others loaf, does the claim of clean shared duty stand or break into uneven reality? Consider torsion from wind and fit-out masses on the Y-wings. The check is torsional strain. Read twist in the core during gusts, and then translate that into edge pile strain to see if rotation loads a flank differently than planned. Think. Reality does not care. If Trist shifts weight onto one set of piles, does the base story of balanced load path hold water or spring leaks? Think about thermal gradients in the raft and pile heads under a desert sun. The check is simple. Match day-night temperature swings at the base to microstrain in the raft, and see if cyclic opening and closing concentrate stress near a few pile collars. Look. Count it or cut it. If daily heat pumps small cracks where piles meet raft, does the steady base claim keep its footing or slip into slow wear? Now, look at installation sequence, because sequence matters. The check is settlement staging. Compare early piles loaded by core jumps to later piles that were capped later, and ask if the first movers locked more load at the start that the latecomers never fully picked up. Be honest. You cannot cheat constraints. If timing alone baked in uneven duty, is the official even share script honest, or a clean line that ignores build order? On friction along the shafts, drag can flip sign when surrounding soils settle. The check is to track relative motion between shafts and soil over years, with embedded markers near the top segment to spot any downdrag pulling added force. Think, measure, then believe. If soil movement starts dragging on the shafts rather than hugging them, does the friction tally stay put, or does it fade where it was counted most? Watch water levels, because water moves strength. The check is to overlay any recorded groundwater shifts with settlement speed-ups or slowdowns, and then ask if low water left soils looser and trimmed friction down. Look. Physics caches the checks. If water ebb lines up with added slump, is the stable layer line still firm or shown to be a moving piece? Follow the outrigger connections, because that is where energy flows. The check is hysteresis. Measure load in and out of outrigger links during gust trains, and chart any lag that hints at slip or play that grows with time. Be honest. What breaks first? If those links show growing lag or slack, does the crisp model of immediate sharing hold? Or is the real building a beat behind when it most matters? The dampers are machines with software and oil. The check is aging. Compare response curves in early years to later years under similar gusts, and ask if damping stayed sharp or got lazy. Think. Stop buying it. If the curve dulls and nobody tells the public, is the comfort story stable or a quiet slide toward thin margins? Sensors, again, are the eyes and ears. The check is overlap. Intentionally run redundant sensors in a few spots and pull one at random to see if the system notices the loss and flags it, or sails on. Look. Do the simplest check. If blind spots slip through, can we trust a smooth dashboard to mean a safe tower, or just a neat picture? Models can be retuned after the fact. The check is to audit revision logs and ask if inputs were changed to match observed settlings, without kicking those changes back into a full recheck of safety claims. Be honest. Reality does not care. If the model was bent to fit the data, but the safety flags were not rerun under the new inputs, is verified by model a lie by omission? Public Lines ranked all of this as established. The check is repeatability. Ask if the same recipe was reused in other places with the same ground profile and climate, and keep count. Think. Who benefits? If the count is near zero, is established anything but a sales line masking an outlier? Settlement that is within limits can still be uneven. The check is plumb truth. Rinse and repeat level runs at the core and the wingtips. Then track angle change and correlate with service reports for doors and panels binding, because those binds are early tells. Look. You cannot cheat constraints. If the building hardware keeps telling us where it leans, is the official calm still believable? Heat cycles load the base daily. The check is to pull microstrain lag between thermal peak and structural response and see if any zone takes repeated peak hits that rise year to year. Be honest. Measure, then believe. If peaks ratchet up in a corner, is the core spreader still doing its job, or is that a slow drift to a problem? Pile concrete that runs hot in a deep hole can form pockets of weakness. The check is acoustic. Tap tests and sonic logs from install days compared to any later non-destructive checks, and then hunt changes. Think. Count it or cut it. If old echoes do not match recent takes, is that benign drift or proof the concrete core was never as even as sold? Construction washouts in sand can erode around casings during pour. The check is volume balance. Compare theoretical concrete volumes to batches actually pumped plus returns and see if unexplained losses align with any later anomalies. Look. Stop buying it. If there were volume gaps tied to certain piles, is uniform quality a safe line or a slick hope? Clusters of piles can block each other's friction zones. The check is neighbor effect. Read strain in a dense patch under live load and compare the outer rings to inner rings to see who gains and who starves. Be honest. Reality does not care. If inner piles lose grip while edges pick it up, does the even share pitch still fly? Or is it broken in practice? The raft spreads load if it stays stiff. The check is curvature. Measure slab camber across the base and match that to how piles engage under live load to see if flex lets some piles off the hook. Think. Do the simplest check. If base curvature shifts pile duty, is the stiff raft an assumption too easy to say and too hard to prove? A tower this tall rides different wind stacks on odd days. The check is storm sorting. Catalogue events by direction plus speed and tie those to structural response. Then ask if any combo hits harder than the model saw. Look. Physics caches the checks. If one quadrant keeps punching above charts, is the wind story solved or thin? Comfort for people at the top is a canary. The check is to pair guest or worker notes about sway with damper status and ask if human comfort comes only when dampers sing. Be honest. Prove it under load. If piece at the top equals machine on, does the passive design merit the praise it gets, or is that praise fiction? Claims that We measured everything, often skip calibration drifts. The check is drift chase. Track long, slow zeros in sensors during quiet periods and flag any that slide without cause. Think. Stop buying it. If zeros walk, can we trust tiny slopes reported as safe? Or are they artifacts of eyes that wander? Talk of factors of safety hides that many were calculated off assumed soil maps. The check is to run a variant model, where the carbonate layer is pocked or broken, and then recheck pile load shares with the same total mass and wind shapes. Look, you cannot cheat constraints. If a modest change in layer smoothness pushes some piles over their comfort line, is the safety claim stable or shaky? Sequence decisions were made to keep going fast. The check is pace penalties. Identify where pours were pulled into cooler hours, or when mixing was slowed, and ask if those spots later showed different behavior under load. Be honest. Measure, then believe. If speed made the schedule, but planted variance we can now measure, does the controlled build line hold or bend? The tail often credits clean inputs for the model. The check is mix variance. Pull records of concrete batch strengths and ask if the lowest values, not just the averages, were fed to the model for safety. Think. Count it or cut it. If only pretty numbers go in, are we modeling the building or writing fiction? Risk was accepted in ways not normal for simple profit. The check is motive math. Stack the tallest title value against the appetite for dampers, deep piles, and bespoke shapes, and see which motive explains more of those choices. Look. Who benefits? If the risk pattern maps to prestige more than to lease sums, is the public line hollow? Everything down there is buried forever. The check is irreversibility. List which defects can be found and fixed, and which cannot. Then, count how many single-point failures hide under the raft. Be honest. Reality does not care. If most real faults cannot be touched, is the claim of controllability honest or impossible in practice? And this is the rub. Neat explanations cut all these variables into calm lines. The check is to pull any single weak link, sensor blind, damper fault, hot pour, loose layer, and hold it against the claim that the margin still stands tall. Think. Do the simplest check. If the tail needs every link to be perfect, is that engineering or a fairy tale wearing hard hats? So here is the verdict. The official explanation fails the audit where it bites. It does not square with the risk appetite, the reliance on active machines for steadiness, the need for flawless buried work, and the pick of a site with 40 meters of sand when easier ground exists. The ceiling check is the split between public calm and the on-site contortions needed to build and keep tune. Look, physics cashes the checks. If the voice of certainty cannot bear its own conditions, is this truth or a careful fiction turning a daring experiment into a Sunday stroll? Here is one hypothesis, and this does not add new facts. It just reframes what is already on the table. The Burj Khalifa doubled as a full-scale testbed hidden in plain sight for technologies that quietly manage mass and motion beyond the classical playbook. It is a testing ground for classified load and vibration control tech. It works by pairing visible engineering with hidden systems that bleed off forces and steady mass in ways the public papers do not name. It fits because the risk profile, the site choice, and the polished calm make sense only if a deeper safety net sat under the show. Think. Who benefits? If the true goal was to prove control at scale without saying it out loud, does the pattern now read as nonsense, or does it finally click? The takeaway is blunt. The official story uses correct parts, but sells them as routine. And that sale does not survive contact with site constraints, moving forces, and the need for perfect execution over decades. The simple next step for you is to keep asking which claims can be proven under load and which demand a spotless chain of maybes, then hold back belief until the hard checks pass. Look, measure, then believe. If you keep that lens on every glossy tale about record-breaking builds, how many still stand on their own feet? If you want more forensic breakdowns that pressure test the stories we are sold, follow for the next deep dive.